Hello folks and welcome to my magic show. My lovely assistant here is about to place in front of me a completely identical microphone to this one that I have right here. I'm going to plug it into this cable which directly plugs in to this speaker. Nothing up my sleeves, nothing in between the microphone and the speaker other than the cable. So you might not be surprised that when I speak into it, it just sounds like my voice. But if I unplug this microphone and instead plug in this one, gonna turn that down a little bit so it's not blasting on your eardrums. Well, that's right, thank you folks, thank you. Oh, please folks, I'll be here all week. Seriously though, I'm doing no post-processing on the output of this microphone. You're hearing exactly what's coming out of the XLR cable. And yes, that autotune did sound pretty bad because I put it on early 2000s T-Pain mode so that the intro of the video would have like an obvious effect going on. But we can do like a more subtle type of autotune like this. Mary had it down. Autotune is far from the only thing you can do. In fact, this thing has a computer inside of it, so you can basically do anything that you want with digital signal processing on the inside of the microphone. Here's like a crazy huge reverb, like in a cathedral or something. And here's like a phaser / chorus type of effect. And perhaps most importantly, here's my dad. You see, I had the idea for this project because a few months ago, there was this girl who was doing this live stream and people thought that she was using autotune in her microphone or something like that, and it turns out she wasn't, and it was a whole scandal, but anyway, it doesn't matter. The point is that it got me thinking, what if you could actually put cheats that were completely undetectable because they were on the inside of the microphone and all of the cheating happened before you got to the output of the XLR on the other side of the microphone. That way, even if you had access to their computer and you can see their entire digital signal processing chain, you wouldn't even be able to tell that they were cheating because all the cheats happened before it got to the cable, let alone the computer. And coincidentally, a few days from now, I have a trip planned to go see my parents, and while my dad is good at a lot of things, singing is not towards the top of that list, and I thought that would be a perfect demonstration of the technology, because if this can perfectly auto-tune my dad's voice automatically, then there's hope for all of us, isn't there? Well, some of you may have seen this demo before, but if you literally just take a coil of wire like this, preferably with something to catch the air, which is what this big disc of plastic is for, and you stick it near a magnet, you can use this as a microphone. So let's try it out. Yeah, it sounds about as professional as it looks. The issue is that the signal is very weak and the noise is very big, right? If only we could hire some smart guy to figure out a solution to both of those problems at once. We'll all be using him soon enough as it is. Classic, nostalgic, it's perfect. So the default way of sending signals down two wires is that you send the signal down one wire and you send a reference, or usually the ground, on the other side. Pretty simple, right? You take the signal, you subtract the reference, and you get the signal. Straightforward. But in our case, if you take a look at the signals coming out of each end of the coil of wire, on one side we have the signal, and on the other side we have the same signal but flipped around. The way you can think of this is that if you look at the coil of wire, the electricity is getting pushed in one direction, but the electricity has to come from somewhere, that's what a circuit is, and so it has to get pulled from the other end. So when one side is getting pushed, the other is getting pulled, and vice versa. So we basically have two versions of the signal coming out of each end, and you could just throw one of them away and send ground down the other side, but what a waste that would be. Instead of doing that, you could listen to some smart guy from a long time ago, much smarter than me, who realized that despite the fact that the signals are opposites coming out of each end, the noise down each leg is actually very similar in most cases. So what you can do is if you take one signal and you subtract the other, well, the signal actually gets twice as loud because you're subtracting like 1 minus -1 becomes 2, but the noise actually cancels itself out, at least in ideal cases. It's like a definition of a win-win situation. This gets used all over the place in like small, precise circuits, and it's called a balanced signal, which is why if you look at like audio equipment, sometimes it'll be called balanced versus unbalanced. But just saying like take one signal and subtract the other is a little bit easier said than done. But how do we actually accomplish it? Well, if you ever took a class about operational amplifiers, op-amps, then you'll have known of something called a differential amplifier, which is a simple way of subtracting one signal from another and then amplifying it by some gain. And it would work, but actually this has a lot of problems that we would really ideally like to avoid. So what we actually have to use is something called an instrumentational amplifier, which is a little bit more complicated than an op-amp setup. These things are literally made for precise instrumentation, which is why it's called an instrumentation amplifier. And obviously our microphone is an extremely precise instrument. Look, the people that invented the chip didn't know that we were going to be making meme YouTube videos with the technology 100 years in the future, so it's a precise instrument, just like trust me, okay? If you want to learn more about not only how the instrumentation amplifier works, but also like build up the intuition to how we get there in the first place, I really recommend this video by Professor Fiore, which is where I learned about them in the first place as well. Link down in the description, of course. So I bought this tiny little instrumentation amplifier breakout board, and when we hook it up to our microphone and speak into it, look, obviously even calling this thing lo-fi would be generous, but come on, this thing sounds way better than literally just a coil of copper wire stuck into my audio interface has any right to be, okay? And more importantly for us, clearly the instrumentation amplifier is working, right? The noise is way reduced, and the signal, although it sounds terrible, is much clearer at least than it was in the first place. This simplest form of a microphone is called a dynamic mic, and if you take a commercial dynamic mic, like this Shure SM57, that's basically exactly what you have. Up here in the capsule is a magnet with a loop of wire, and then it sends the signal down in a very similar way to the way that we've done it. Obviously, a professional microphone is going to be a lot better designed and implemented, though. Obviously, they're not going to be using Kapton tape to hold their stuff together. There's not just going to be like a giant glob of hot glue inside this thing holding a bunch of mechanical parts, right? Look, you guys can probably already realize I'm a huge Shure fanboy. I love these things. But come on, what mechanical engineer looked at this and decided, yeah, you know, we just gotta use the same thing as I used to stick my shoe back together when it falls apart. Yeah, that's all. At least up at the capsule, these two wires are basically what we expect. These are equivalent to the two wires coming out of my loop of wire microphone. Okay, so that's the first part of step one done. We know how to get the signal out of the microphone. But what about the space constraints part? Well, we're gonna have to do something about this whole hot glue mess. And thankfully, actually, back in the day, getting rid of this hot glue used to be a pretty popular mod with SM57s because all the hot glue is doing is holding down this transformer that arguably the microphone sounds better without. It just has less gain, but it clears up like the low end, whatever, and it doesn't matter. So let me just follow this recipe and...
Today on The French Chef, we're preparing transformerless microphone. Take your bagged microphone.
I just wanted to do a Julia Child impression. I'm sorry, I stole this joke from this guy. I can't even pretend. So anyway, now that that's over, we have this beautiful empty cavity to work with, which is definitely way smaller than it seems like it would be from the outside, but that's okay. So for this, we're gonna need a really small computer. What is this, a computer for ants? This right here is an ESP32, and despite the fact that it's like literally the size of one of my fingernails, this thing is actually a pretty legit computer. It can run it up to 240 megahertz and has several CPUs that you can run in parallel, and we're gonna need to use all of that because to process an audio signal, you need to run at at least 40 kilohertz, Nyquist theorem and all that. CDs are 44.1 for example, and so with the maximum CPU clock on this guy, we have like roughly 5,000 to 6,000 clock cycles in order to do all the processing per sample, which sounds like a lot, but trust me, it really adds up fast. So we're going to skip this little section of the plan for now and move on to this last step, the outputting step, so that we can actually test out the full system and see how it sounds right now. So what we can do is we can take in that signal that we're reading from the instrumentation amplifier, and we can just, with no processing, spit it out on one channel, and then on another channel, we spit out the exact same signal, but we just subtract it from one. And if you just hook that up correctly to the prongs of an XLR cable, you have a beautiful balanced signal. Let's give it a test, shall we? Yeesh, wow. Okay, well the good news is that you can hear me talking, and the bad news is that you can barely hear me talking over, all the rest of that stuff. Okay, so a couple things to investigate on fixing it. First of all, allegedly everybody on the internet says that the DACs on these chips are really bad. So let's get a breakout board for the DAC. Let's take a listen.
I'm very much hoping that this one works. Mary had a little lamb.
It sounds like a little better, I guess? But that means that we're left with a much bigger problem. And honestly, this took me forever to figure out. I had to scratch the depths of my brain to get back to one college signal processing class that I'm pretty sure I took. I learned this concept and I immediately forgot it. And what is it? It's the gain bandwidth product. And what is that, you may be saying? Well, the gain bandwidth product is, it actually sounds pretty scary, but it's really simple and straightforward. Basically, if you're using op amps to give amplification to a signal, you're always going to have an inherent trade-off between the gain that you have, or the amount of volume that you're adding to the signal, and the bandwidth, or the range of frequencies that you have. So if you take the gain that you want and the bandwidth that you want, and you multiply them together, you get a product that just has to be less than the gain, bandwidth product for the chip. Problem with this microphone setup is that we need both really high gain. For the SM57, we need ideally like 500 times gain. But at the same time, you need at least 20 kilohertz of bandwidth. And this chip that I tried claimed to have 6 megahertz. And you know, that would be just on the cusp of acceptable, but I think this chip is lying. I think it's actually lower than that, at least in practical circumstances. So I had to get this fancier chip that is much bigger and has these huge potentiometers that we have to somehow get rid of at the end product. But it claims to have a much higher gain bandwidth product. And so let's try it out and hope that it sounds better.
Test, test, test. This is a test of the microphone.
Wait, do you know what you just heard? Did you say the radio? Because yes, you heard the radio, but open up your mind a little bit and you'll see that you actually heard the sound of an extremely solvable problem. That's right. After a week of scratching my brain, having no idea what was going wrong and why it sounded so muffled, it sounds super clear, other than the noise and the radio talking over the top of my voice. But those problems are just electromagnetic interference. There's just noise coming from the airwaves. And so there's a super simple fix to both of these. First of all, if you don't want to hear the radio, then maybe don't make your entire thing an antenna. That's right, just having these huge long exposed wires basically acts exactly like an antenna that you would have on your car or on like a handheld radio. And so that's why we're picking up the radio. And if you don't want a bunch of static noise interfering with your signal, then you should put it back into that metal casing of the microphone. That's right, most audio equipment is made out of metal, one for a premium feel in the hand and whatever, but trust me, a lot of these companies would happily be using plastic if they could save on costs. No, they have to use metal because it acts as a Faraday cage, and so just having the signal encased in metal is enough to get rid of almost all of the noises coming in through the air from around the room and into the signal path. So let me just clap my hands and bang! Suddenly all the chips have magically been soldered to a perfect little package. Except not really. Actually, let me show you what really happened is I clapped my hands and I've been soldering for like 2 days. Like actually, I've just done nothing but solder for 2 days. This is horrible. And like, it's so fiddly and frustrating, and you have to solder these like tiny little wires that are like 2 millimeters long.
Okay, but seriously, I did want to show off the final product a little bit. Look at all these tiny little solder joints. It's not pretty, but I can't claim to be great at soldering. Also, this thing barely fits inside the microphone cavity. I legitimately think that when the capsule is screwed back on, that there's maybe like 1 cubic centimeter total empty inside the whole mic.
And I didn't just put this part in to complain about all of the fiddly soldering I had to do, but also to complain about the fact that actually, at the time that I was soldering these things, I had literally like a few hours left until my flight. Remember that I'm going to try to bring this thing to use my dad as a guinea pig, and I have like 4 hours at this point, so yeah, let's get to it. So I cross my fingers while I force the chip into one side and the XLR jack back into the other side. I'm gonna plug it in. If this doesn't work, I have a few hours left till my flight, so I guess I'm just screwed.
Okay, this is a test. I'm recording. Mary had a little lamb.
It worked! It works with a few hours to spare. Oh my god, it's like actually like a story. Oh my god, this is by far the most effort I have ever put into just making something do literally nothing. Like, I don't even know what second place would be, but it definitely doesn't even come close. But the beautiful thing is that now that we have a microphone that does nothing, we have a microphone that can do anything. That's right, now we have taken this hardware problem and we've completely reduced it into just a software problem. We can now program this chip. Thankfully, by the way, you can stick a little tiny USB-C cable into here to charge the battery and program the thing. And since we can program this ESP32 to do whatever we want to the signal before we send it back out, well, that's where all the digital effects live. Let's start off with something simple and just filter my voice. So we're going to talk into it, and it's going to use something called a biquad filter, which is a simple algorithm to get rid of some frequency bands that you don't want.
This is without any filtering! And this is filtering at 1000 hertz.
And yep, it sounds like it's doing pretty much what you want it to do. But it's time to get to the main event, isn't it, right? The autotune, what we've all been waiting for. And if you've watched any videos about audio processing, like me, you might be thinking of 3 little letters immediately right off the bat. And those letters are FFT. That's right, the fast Fourier transform. I was so sure that the FFT was going to be the solution to our auto-tuning problem. This is the only part of the script that I pre-wrote, and guess what? I had to delete it all because the FFT is not a good solution, at least to the way that we have the problem set up. I'm not going to give a full breakdown of Fourier transforms in this video. 1, because there's plenty of videos that do it better, and 2, because, well, we don't actually use it in this project, and I'm sure there'll be a project in the future where I end up using it, and I'll explain it then. But really quick, suffice to say that it takes a signal and it turns it into the frequency domain. So if you have just a waveform waveform like this, you can get the frequencies that make it up out here. And this would be really great for us because we would be able to get the frequency that you're singing at, right? So for example, here's the waveform of me going, ah! This big spike here represents the dominant frequency of the audio that you're sampling, and that is also known as the pitch or the note that you're playing. And the rest of the smaller spikes are known as the overtones. And the overtones are what separates, say, my voice singing that note versus a piano playing the same note or a car engine that happens to be playing that note or whatever. The thing is that for a simple autotune, we don't need all of these overtones. We just need the pitch, the big dominant spike, and all of this other stuff is not only wasted computation that we don't have the liberty of doing, but also because we need to focus on all of that, the digital nature of it means that our bins, or like the little bands of frequencies that we're analyzing, are way too big. Like for example, in the first FFT I tried, the bins were 10 hertz, which doesn't sound like a lot. But in terms of pitch, that's huge. Like at lower octaves, that's like a whole semitone. That's massive. It turns out that there's a better algorithm for simple auto-tuning that was made in the early 2000s, and it's called the yin algorithm. And it works basically in like the simplest way you could possibly imagine. You take a little chunk of the signal and you start moving it around. And as you can see, when you move it around, if you subtract the moved signal from the original signal, you get this big difference. And as you move it around, because our audio signals repeat really fast, that's just kind of how audio works, once you get to the next peak, you're going to have a really small difference because they're going to look very similar. So if you just take the amount of movement that you need, that gives you an amount of time before the signal repeats. And now if you just take 1 over that amount of time, you get the dominant frequency, the frequency that it would require to make that big spike. This turns out to not only be like way easier computationally, but it actually gives us much better, much finer tuned results than the FFT would have. Okay, so all we have to do is implement the yin algorithm, and what that algorithm is going to give us is the frequency that we're currently singing at. All we have to do is take each chunk of the singing and make it slightly faster or slightly slower, and that changes the frequency that you're singing at. And with some simple math, the amount of stretching that you're doing can basically immediately map it onto whatever note you want.
One flight later.
To test it out, we finally got my guinea pig here. I had to pick songs that will hopefully avoid copyright claims because apparently that's the thing I have to worry about now after my last video. And what's more fair use than a true American classic? Mary Had a Little Lamb.
Oh, Mary had a little lamb, a little lamb, a little lamb. Mary had a little lamb with fleece as white as snow.
Okay, but to give my dad a chance to be a little bit closer to his roots, we next picked an old Soviet folk song called Черные очи.
Очи черные, очи страстные и могучие. Очи жгучие и прекрасные, как люблю я вас, как боюсь я вас, знать увидел вас я в недобрый час.
And thank you very much to my dad for being such a good sport about this, but there's a bit of an elephant in the room, which is, well, the autotune didn't sound super great, did it? In fact, in some parts, my dad's original singing without the autotune probably sounds better than the autotune version. And look, of course I could blame that on autotune itself just sounding bad, and things like the further you are from the note that you're autotuning to, the more robotic and jittery that it sounds, and so if my dad was closer to the actual note, then it would sound better. But those are really just excuses, let's be honest. In reality, I just didn't want to spend all my time during my visit to my parents just working on like an autotune algorithm, and so I was happy to get anything working at all. And so when I got home, I tried to improve the algorithm a little bit and get it sounding a little better. Let's see how that sounds on my vocal now.
Очень страстное, очень жгучее и прекрасное, как люблю я вас, как боюсь я вас, знать увидел вас, я не добрый час.
And look, it's still not exactly state of the art. If you wanted to do something fancier, you have to do stuff like format matching, which would require that FFT approach that we were looking at before. You would take a look at all the overtones and you try to add them back in and take them into account. But that's probably not really something we can do on this chip, and if we could, it would require like John Carmack levels of optimization. And look, I'm a bit of a perfectionist, so I'd like it to be better, but as far as a proof of concept of sticking autotune into a microphone, I think this does a pretty good job. Also, honestly, I mean, I picked autotune because it's like computationally expensive, and so it's like difficult to do on the small chip on the inside of the microphone. But honestly, as I've been playing around with the other effects, I think they're actually cooler and more impressive. So for example, here's like a super effect where I'm doing reverb and echo and that little chorus thing that I was doing in the beginning. So anyway, I don't know, I think it's cool. I guess the other thing that I would like to cover is the idea of like actually using this thing to cheat. I don't actually want people to use this type of technology in like a cheating environment. I don't want people to go on stage and pretend like they're singing but actually have autotune on the inside of their microphones. But the issue with that is if you're worried about this, well, you're already too late, unfortunately. You see, live autotunes existed for a long time. It just has to exist on some outboard gear. You usually have to have it on some separate computer. The point for me was just to make a challenge of like, can you get all of that stuff on the inside of the microphone, which is kind of crazy and space constrained, and it was kind of a fun little electronic engineering project. But in reality, if you want to cheat, there's much smarter and much better ways of doing it, and you can do it on like a legit computer that can run any algorithm you want in much faster speeds. The thing that I think makes this project more cool is that, you know, you could take it to like, theoretically, I don't know, karaoke bar or your friend's house or whatever, and you plug it into their speakers, and then all the tune comes out the other end, and you know, oh man, how did that happen? But in reality, my magic show intro, well, it really is just that. This thing is kind of just like a fun little party trick. So I don't know if that makes you feel better, but it does make me feel a little bit better thinking that this thing is more of a party trick than like some actual evil invention. As always, thank you so much for sticking around to the end of this video. I really hope you enjoyed. This is normally when I would like to have like a big scrolling list of the kind comments from my past video, but my past video blew up way more than I expected, and I got like so many nice comments, so this is just going to be a selection. Thank you so much to everybody that watched that video, and especially to all the people that ordered a Fredlock. I thought I was going to sell like 2, and I ended up selling out, so spent several weeks learning how to operate a small business. That was fun. But anyway, if you haven't seen that video, I will put it in the end card. You might want to check it out. It's kind of like a fun prequel to this one. It's a little bit different, but it's got similar flavor. But of course, even if you hadn't heard of that video, thank you so much for sticking around to the end of this video. If you really want to help me out, it would help me a lot if you liked, subscribed, commented on this video. I would really appreciate it. But in any case, thank you so much. And as always, I'll see you next time. Bye-bye. Am I a theater kid? Like, did I really need this cape for the 15-second YouTube intro?